we welcome the next speaker. It's Frank Deppe. He's not a relative of mine, if the last name is the same. Sometimes I'm asked because he's also working in Munich. So he is group leader of the group Superconducting Quantum Circuits at the Walter Meissner Institute in Garching. So it's near to Munich. And his talk is about microwave quantum teleportation. So the stage is yours.
Thank you very much, Christian. It is indeed rare to find somebody of the same name in the same field. Thank you very much for the nice introduction, and thank you for the opportunity to present our recent results on microwave quantum teleportation here in this workshop. I think you can find a lot of details here in this reference on the bottom left. And since most of your community will not be, of the listeners may not be accustomed to the details of the microwave community, I will try to be pedagogic. Okay. So first of all, about microwaves themselves. Classical propagating microwaves are omnipresent in our everyday life, actually. So, of course, in the communication via the cell phones we all use, but also in sensing, for example, in radar, or when looking into deep space. There you also want to look at microwave frequencies. And of course, when we discuss about our standard computers, and especially about supercomputers, then microwave communication and microwave signals play a big role. And the underlying question beneath our research is now how to apply quantum microwaves for enhanced performance in such fields. What are propagating quantum microwaves? I will focus on a very specific type of propagating quantum microwaves. And these are especially a Gaussian type of entanglement, so-called two-mode squeezing. The frequency range is approximately 6 gigahertz. I will explain later what this generation picture means. For now, this list of references and the pictures are just meant to say that we know that we are doing this since roughly 10 years. So we are pioneers in this field, and that we actually do know how to create such quantum resources in the microwave regime with a high degree of control by now. Now, of course, microwaves, as you see from the frequency, have a low photon energy, which is often considered a disadvantage, but can be nicely counteracted by going to cryogenic environments of the millikelvin scale. So this you can still buy commercially, such fridges. On the other hand, microwaves have a lot of positive and chocolate sides. So they're the natural frequency scale for radar and for superconducting quantum processors, which are very successful these days. And this means when trying to use them in this context, we will not have the otherwise omnipresent frequency conversion losses. The next thing is that our microwave, the underlying technology, allows for strong coupling. And this means that we can do many protocols in a deterministic fashion, which is also positive. And then we have to discuss, of course, propagating, how to transport these states. So we have superconducting cables, and we have found actually losses from commercial, totally unoptimized cables of better than 2 dB per kilometer at this frequency. So this is not far away from standard commercial optical fibers. Of course, not the best ones, yeah, but from standard ones. And we can even expect a free space range of roughly 500 meters. And then we can think about possible applications, which could be the distributed quantum computing. So probably the first step would be some kind of quantum local area network between such devices. There are many proposals about quantum radar type sensing, where quantum microwaves would make a difference. And of course, once we are at it, we can also think about quantum communication via our superconducting cables or via free space microwaves. We can also think about microwave QKD and such things. The talk now will be focused on continuous variable regime because this is my particular field of research. And how do we create such devices? Actually, we use LC harmonic oscillator, so just a resonant inductive and capacitive circuit we can do very nicely with superconductors. This is linear, but then we add a so-called Josephson junction, which you can consider just as a nonlinear inductance. So this is our nonlinear medium, and when we combine these two elements on a chip, for example here, so the yellow color is a niobium film. The junctions here, the Josephson junctions, are typically made of aluminum. Then we get a nice quantum circuit, and if we do it the right way, then these will emit propagating quantum microwaves, and in our case, or for the purpose of this talk, in the continuous variable regime. So how would we imagine that? Of course, the easiest classical picture is a cosine wave, and the cosine has an amplitude and a phase, but we all know that these are not very nice variables because they're so different in character. So we typically rather re-express this in terms of the field quadratures P and Q. And as I said, the typical frequency space, the region is around 6 gigahertz. So we can now look at the state and the phase space of these field quadratures, which are our conjugate quantum variables. And in a classical case, a state would simply be, in the absence of noise, a point in such phase space moving on some trajectory. Again, we all know that quantum mechanics is different. We have the vacuum fluctuations dictated by the Heisenberg uncertainty relation, or equivalently commutation relations between the field quadratures. And for this reason, the ground state is the vacuum state, has actually a finite probability, a finite Gaussian probability distribution with a certain vacuum variance. Now, this is not carved in stone because we can indeed squeeze or squeeze this variance in one quadrature direction. So here I choose this somewhat 45-degree angle direction in the picture below this vacuum limit, but then we still need to respect the Heisenberg relation, and the uncertainty in the orthogonal quadrature will increase. This is a so-called squeeze state. We have heard about it many times, and it is a quantum resource, and it will be the quantum resource for this talk. Now, how do we generate this? The main building block is called a flux-driven Josephson parametric amplifier. What we do there is we take a superconducting resonator, here this structure on a chip, and we shunt it to ground with a suitable set of Josephson junctions. And then this you can also see here in this circuit diagram. Here you see a circuit diagram of the distributed element resonator, and here so-called DC grid. So this is essentially a tunable nonlinear inductance. In addition, we allow for a pump signal to be applied. So here via this port. And then, of course, we have an input and output port, and we use only one port and separate the in and outgoing signals by a directive element, a so-called circulator. And we will, since this is often used as an amplifier, we use an amplifier as a circuit symbol. But here we want to use a squeezer. So what happens? We can put in the vacuum state as input here. And then we can actually pump with a strong coherent tone at twice the resonance frequency here on this tunable inductor. And as a result, as an output state, we get a squeezed vacuum state. So here you see that the variance has indeed been reduced. Here the blue curve in one quadrature direction below the vacuum variance and has blown up in the orthogonal direction. And to make the long story short, this is a picture of how the chip in the sample holder looks. Yeah, this is sort of the The black thing is the chip. And here you see that we use a coil and we use some thermometers for temperature control and heaters, and we put it in an aluminum box to protect them from spurious environmental signals. And we achieve something like up to 8 dB of squeezing on a regular basis. Now, squeezing alone is not entanglement yet, so we need what is called two-mode squeezing, and this we can easily generate by applying 2 such Josephson parametric amplifiers acting as squeezers, having them squeeze in orthogonal quadrature directions, and superposing the signals at a beam splitter. And in microwave terms, this is a so-called 180-degree hybrid ring. As a result, we get signals which in each single path, so what you see here are actual experimental Wigner function reconstructions in this PQ phase space. And you see that they look somehow thermal, which is expected for a balanced two-mode squeeze state. The single path do not contain any significant information. But if we now look at the phase space involving either Q1 and P2 or P1 and Q2, so from the 2 different paths, 1 and 2 here, the output path, we see that our squeeze quantum correlations have been moved into these into these entanglement correlations. And so we get typically a similar degree, roughly 8 dB of two-mode squeezing in regular operation. Now, as a last part of the introduction, since most of you will not come from the microwave community, I wanted to give you a small dictionary of the used symbols. We are used to that, but there's often a somewhat one-to-one correspondence in the diagrams. So what you always use as referred to as a laser, in our case, is also a commercial device of high coherence. It's a microwave generator. You can buy this, and it's commercial because it's widely used in the mobile communication, of course. And it has very low phase noise. It's really comparable to high performance lasers. Then what you would refer to as a nonlinear crystal or nonlinear medium, in our case, is the so-called Josephson Junction. So this is a particular superconducting junction where a small insulating barrier couples 2 superconducting electrodes, and we treat this in circuit language as a nonlinear inductance. Then some of your experiments may use optical parametric oscillators. You can, for us, this is what I introduced as a Josephson parametric amplifier, so a quantum swing in a way. Interestingly, the parametric amplifier is a very versatile device. So what you would call as a homodyne receiver, which actually can detect a particular quadrature of the quantum field. This is we can again use the Josephson parametric amplifier for that. What you refer to as optical, or what you use as optical fiber to transmit information, we would use superconducting coax cables. I commented on that. The beam splitters, we also have as microwave elements, for example, a hybrid ring beam splitter, as you can see here. And also things like a 99% reflective mirror has a direct counterpart, is a directional coupler. There are some more, but I focus on the most important ones here, of course. Okay. With this, I want to move to the main part, which is which are the results of our experimental quantum teleportation of propagating microwaves. So the task is that Alice wants to transfer an unknown quantum state to Bob in teleportation. So she could use a direct straight transfer, which would work, of course, with our cables, for example. But then this has the severe disadvantage that it has the advantage it's simple, but it's somehow insecure because an eavesdropper Eve could sit somewhere at the middle of this cable and just intercept this quantum state. And the way out of this is obviously to do teleportation. This is very general, where Alice and Bob share an entangled resource here. They have pre-shared entanglement. And then Alice actually mixes this state with her part of the entangled resource. And so she doesn't have to know the state. Then she does some kind of Bell detection scheme. And the result of it, she communicates via classical feed-forward channel to Bob. Bob will do a local operation and recovers this state. And again, Bob doesn't need to know this state. Yeah, he can just send it on. And it is still secure, and it is now secure in a sense that an eavesdropper Eve cannot use the classical feed-forward signal to have any implication or any information on the quantum state if we do it right. And this is, of course, a very fundamental quantum communication protocol and can also act as a remote gate. So it is obviously first task to do. Now, this is very general. Our particular implementation has to refer to the microwave ideas. So we use actually two such parametric amplifiers operating as squeezers here to generate squeeze states. And then we superpose them on a 50-50 beam splitter, which is our quadrature hybrid ring. And then we have the two-mode squeezed resource as an output. This explains now the picture we had in the very first slide. And here you see once more that the JPA is symbolized with this triangle. Then, of course, we need to generate an input state. In our case, this is a coherent state, so also a Gaussian state. And Alice needs to generate the feed-forward signal via using her part of the resource and superposing it with the at another hybrid ring beam splitter. And then actually amplifying two orthogonal quadratures, P and Q, with two JPAs with a relatively high gain, G. And so in a phase-sensitive way, and recombining this signal and then sending it to Bob. And of course, Bob also has received the TMS, so the two-mode state idler, the second path of the two-mode squeeze state. As I said, this all happens at 50 millikelvin. And now our feed-forward signal is just a 42 centimeter wire, so coaxial cable. So this is the rough distance, 0.5 meter over which we teleport. And Bob's local operation is now just such a 99% reflective mirror, or in microwave terms, a directional coupler. And then, of course, we want to look at the output state and calculate fidelities and the like. And the experimental complexity is now 4 JPAs, so that's comparable to like a 4-qubit experiment. Okay. Good. Now, the actual setup looks like this. This is the 50 millikelvin stage. You see here the aluminum boxes are the JPAs. There are 5 of them, but we use only 4 of them. We see Bob is here the direction. That's Bob, the directional coupler. So this is how Bob looks in the microwave world. Alice looks like this. This is her feed-forward mechanism. So she has the 2 JPA boxes. And then we need 2 more to generate the 2-mode squeezed resource. And of course, we have a few of additional components and wiring and a receiver to do tomography and the like. And I don't have time to go into all these details. So if you compare this to the complexity of the optical tables we've seen, it doesn't look that super complex. It's, of course, still it's not trivial. Yeah. Okay, now we want to move to the most interesting part, which are the result. And let's look at the top part where we here look at a very particular example where we have a displacement of roughly 2.7 photon in terms of photon number ND, displacement photon number ND. And then we can reconstruct our input state, and we see a very beautiful coherent state with a very well-defined phase. So you see here this offset in a certain phase direction from the center of the phase space here in this Wigner function picture. And then we can do the same thing for the teleported state. And you see that we still recover a somewhat coherent signal. It is obviously slightly different, but the fidelity is still 59%. So this is better than the classical threshold of 50%. And if we turn off the quantum resource and sort of do a classical version of our protocol, then we see that indeed here the fidelity drops below 50% in this classical threshold, which is not considered useful for most quantum protocols. And then we can consider, we can examine this in a little bit more detail, and we see that we can actually, if we don't go to such high displacement photon numbers, we can even violate the 60% fidelity or exceed the 66% fidelity, which for Gaussian states is the no cloning threshold. Here on the right hand, you see sort of the angle dependence when we change the angle theta d of this state, and you see that it's almost flat, but there's a small crosstalk. Which makes still a small angle dependence. Okay, maybe I skip the theory model and just say that we have a nice model which models our data very well. This is here this is here shown in the middle of the picture. So the solid bars are actually the fidelities in the parameter space of gain of our feed forward and squeezing of our two-mode squeezing of our resource. And then we see actually that we can we cover quite a nice part of our model in theory, and that we approach very nicely this optimal point under our given experimental constraints. We are not exactly there, and the reason why we haven't come closer, one of the reasons, is that each of these data points takes a couple of days to take. Yeah, so it's not a trivial measurement. With this, I want to give you I want to use maybe 2 more minutes or 3 more minutes to give you an outlook on our general activities of quantum microwave communication and sensing, in where this teleportation experiment is a first step to. So, of course, we have characterized commercial niobium titanium coaxial cables in a scalable way. So we have 2-meter sections which can be actually connected by high-quality joints, and including all effects, we get these 2 dB of losses per kilometer at 6 gigahertz. So this is very nice and very encouraging. And this means for any practical distance, short distance at the time being, this is not limiting. The second is the cryogenics, which is always not believed, but is almost solved. So we are not the only group working on that, but we are in the framework of our flagship project QMIX. Our industry partner Oxford Instruments has designed such a cryogenic connection between 2 millikelvin dilution refrigerators. Here you see the half link. So here you see 1 dilution refrigerator, and you see sort of a central relay station where one could essentially join up to 4 of such dilution refrigerators. And the distance is 3.3 meters, and the midpoint temperature here is 35 millikelvin. The temperature in the fridge remains below 20 millikelvin, I think on the order of 10 to 15 millikelvin. Of course, it's somehow complicated. It's a geometric topological problem, but this can be overcome. And we have just started to connect this half link at WMI to one of our own refrigerators. And so now we have assembled the full 6.5 meter link, and the assembly first characterizations are in progress. Then we have started a project on quantum radar. There we actually want to use continuous variables again, and it turns out that there.
Interrupt you there.
Yes. Can I spend 1 more minute maybe on the talk? Or should I wrap up? Hello?
Just finish the talk and then we come back to the
yes,
okay.
Because it's almost the last slide. So just mentioning that there one can also achieve a quantum advantage in the practical circumstances of up to 3 dB in radar type sensing with these resources. So in summary, we have demonstrated quantum microwave teleportation over 42 centimeters distance. Ongoing experiments and projects work towards a quantum local area network, proof of principle, quantum radar, and we are thinking about, or we are working on microwave QKD ideas. And future goals are, of course, advanced quantum communication protocols, a quantum microwave, thinking about a quantum microwave repeater element for longer distances, working towards quantum local area networks of superconducting quantum processors, and also ideas towards free space quantum microwave communication. With this, I want to thank everybody in the superconducting quantum circuits group for their hard work, and thank you for your attention.
Okay, thank you. So before we come to Ferdinand's question, perhaps first our standard question, which we record. So what do you think will be the first use case for the entanglement-assisted communication networks?
Yes, I would like to split the answer to this question in two parts. So I agree with most people that for the transfer of classical information, probably QKD will be the first one. But now focusing on the transfer of true quantum information, there the question I think is less clear. And there, in my opinion, a quantum local area network connecting multiple superconducting quantum computers is a very good candidate for first use cases. And my argument for that would be that technological challenges are comparatively low, so we don't have to solve the complication of efficient microwave to optics conversion, for example. The cryogenics is solved essentially on short distances. And that quantum computers of superconducting circuits just develop so fast and with so much industry effort, and this will also profit. A lot of technical problems will be solved in that way.
Okay, and what is the current main challenge in your field to realize this?
Yeah, and there I would focus on the second part, so on the QLAN, and I would see no fundamental roadblock here. This is something I really want to emphasize. It's merely technical, and especially I don't see any major roadblock for devices of this noisy intermediate scale quantum device era. In particular, the cryogenics is not a challenge, but the main challenge then is probably the implementation of sufficiently low loss chip to cable interconnects, a little bit better quality resource states, something like that. But such things will typically be required for the superconducting quantum computers anyways. So I expect that we will profit a lot from the industrial efforts there.